All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Krystian Zieliński. He is the lead data scientist at INVICTA R&D. Please join me in welcoming him to our virtual stage.
Hello, everyone. My name is Krystian. I'm a lead data scientist at INVICTA Research and Development Center. And today, I would like to talk about how we used AI for a solution for targeted hormonal therapy during the IVF treatment. So first of all, very quick introduction to the IVF. As you already may know, IVF is a multi-step process. It takes time for a couple to actually be qualified for the program. So I won't go into the details of that, but I would like to tell you what we focused on mostly. So there are two crucial steps when it comes to IVF. The first one is choosing the best IVF protocol for a patient, and the second one is choosing the right doses of gonadotropin. Gonadotropin is a hormone that helps to produce M2s, so those are mature oocytes, also commonly known as eggs. So after the stimulation, this whole process, those mature oocytes are being fertilized, forming embryos and transferred into the patient's uterus. So why we actually focused on those two steps related to the stimulation? Well, basically, the more M2s are collected, the better it is for a patient, because more M2s means more chances to undergo IVF with a single hormonal stimulation. So our goals were to inform the gynecologists about predicted number of M2s for a patient, and also to assist those doctors with selection of proper IVF protocol and gonadotropin doses. So our first approach was to use our data that we collected at INVICTA, which is over 13,000 of IVF processes for 8.5 thousand of patients, to build a model that would predict the amount of M2s for a given patient, for a given stimulation. So for that, we had over 400 clinical factors that we had to choose from, the proper indicators for M2 number. So this is the snip of our data set that we had. And for choosing the proper features for the model, first of all, we trained like a trivial model. So prediction for every patient was just the average number of M2s in our population. And then based on the discussions with gynecologists, we were adding iteratively a subset of features to our model. We're checking if the round mean square error was reduced. If so, we used the feature in later stages of modeling. And that's how we found 7 different clinical factors that helped us to predict number of M2s, which was anti-miliary hormone, so AMH, the patient age, number of M2s from previous process, polycystic ovary syndrome, number of antral follicles on first day of stimulation, and also the selected protocol itself. So we done the modeling in light gradient boosted machine framework, which is a boosted-based method. As you can see here, we obtained round mean square error around 3.8. And for the explanation of the model, we use the Shapley values. Clearly, from those graphs, you can tell that AMH was the main deciding factor of the prediction, together with AFC on the first day of stimulation. Surprisingly enough, the patient age was not such important indicator of number of M2s. And we could stop with that and basically use this data for prediction of M2s. But we went one step further. So we gathered the data, the genetic data for 450 selected patients and ran the test to choose to find the genetic markers that would indicate the number of M2s for given patients. We checked 14 genes that we already knew were related to infertility and found different gene variants there. So there were like 700 different gene variants in our data set. Each gene variant was treated as a different factor, basically. And we tried to correlate it with M2s obtained by a given patient. We used like 13 different techniques to detect the most important gene variants. I won't go into the details of each method because we don't have so much time, but I will tell about two approaches that we found the most success with. So the first one is self-organizing map. So it's unsupervised neural network algorithm that we applied for grouping the patients together that characterize themselves with similar genetic code. So we used only the genetic data, and from the visualization, the two-dimensional visualization of the results of model, you can tell that one neuron is basically corresponding to a group of patients with similar genetic variants. The color of each neuron corresponds to the share of observations in the node from given M2 group. So we found out that there is a neuron with very high share of patients with the lowest M2 count. And for those patients, we found out that there were 6 the most frequent variants there, which we used in the later stages of the modeling as an indicator of having low number of M2s. So that was the first approach. Our second approach was searching for haplotypes in the genetic data. The approach was different in a sense that other than correlating the genetic data with number of M2s, we rather focused on the position of genetic variant on the code, because the closer the gene variants were, the more probability that they should happen together. So thanks to this approach, we found out 3 different haplotypes, which also had strong correlation with M2 count. So we added this data to our data set and checked if the model would predict number of M2s with better accuracy. And that was actually the case. But also we went one step above that. Instead of using light GPM, we also tried out the deep neural networks with use of TensorFlow framework. So those two changes combined resulted in increasing the efficiency of the model by over 10%, for some patients even over 50% of the accuracy. So we have the model that can predict the number of M2s, but how we actually used it in practice. So thanks to the Shapley values, we were able to provide doctors with explainable results of the model. So in this exact example, we could say that if the patient age will be 33, so it's quite low, those patients would be quite young. This would indicate that the number of M2s for the patient will be higher than the average by 0.06 oocyte. So it gives the explainability layer for the doctors. And for the suggestion of proper protocols and proper doses, we use different kernels that differentiated those predictions for different doses and protocols, respectively. So the doctor can see what's the gain of using a certain doses of gonadotropin. Yeah. So we have the model, we have everything in place. So how to actually use it in practice? For that, we can say that we forged the solution using fast API framework together with PostgreSQL database. And we Dockerized the solution to provide a proper solution to the developers. So basically, our approach takes the data of the patient and gives the predicted number of M2s. We built a user interface for that, and right now our gynecologist can simply use the model to explain the number of M2s that the model predicts, and also choose the proper doses and proper protocols for a patient. Yeah, so that would be it from my side. I hope you enjoyed the session. Thank you so much for tuning in. And if you would be interested in how we actually use the AI or maybe some additional technical questions, you can reach me out. You can email me at Krystian Zieliński at invicta.pl, or you can find me on LinkedIn. I'm there to help you. So thank you very much.
Wow, thank you so much. That was amazing. If you could stop sharing your slides, I know this virtual audience wants to give you a huge virtual round of applause. Thank you again for sharing with us today. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.